Hello everybody. You will have to forgive the lighting and angle being somewhat suboptimal, as this is just too big to fit under the camera. It usually would be attached to the ledge. You can probably just about see the top of the frame if I tilt the camera up slightly. It's usually attached to this clamp, but with this underneath it, the camera sticks down too far to fit. So this will have to do for now. This here is a bit of a mystery, honestly. I have a guess as to what this is, and I'll go over in a second, but I'm not sure. This was being sold on eBay as unidentified vintage test equipment, basically, and sold as untested, not knowing what it is. It was like, I think, 20 quid I paid for it, which I thought was fairly reasonable. I think this is probably... The case of this is very much 1960s, but this meter here makes it look newer, so, and this knob as well is sort of 70s-ish, so I'm going to guess 70s, but not sure. I think this is probably DIY or custom made, because it is not actually, it doesn't have any markings on it that identify what it is, other than on the side we have, somewhat curiously, Cornwall County Council, and then various pat testing stickers on the side. This says serial number, but I think this is an asset number rather than the serial number. On the back and the other side there are no identifying marks, and same on the bottom, again, no identifying marks. If we have a look here, the plug, if you can read it on the screen, the plug has a pat test on it dated 2023, which means this was probably still in use fairly recently, so hopefully it still actually works. Now, in terms of what this actually is, I will give you a second, you can stick your guesses in the comments. There is a analog dial up here which measures milliamps. It goes between 0 and 1, with the scale going 0.2, 0.4 and so on. There is a rotary switch down here. This is not a dial, it is a switch, labelled MHOS, and the values on that are, if I read them, 0.1, 0.01, 0.001, 100 micro, 10 micro, 1 micro and 0.1 micro. And then there is this big dial here, unlabelled, with a somewhat strange scale on it, which is almost logarithmic. There is an unlabelled switch at the top, 2 positions, and 2 banana plug output jacks. I think this is probably a conductance meter, because this marking here, MHOS, is the old name for the unit of conductance, which is the Siemens, which conductance and resistance very similar. I'll get more into what the difference actually is. It's fairly minor. As to why Cornwall County Council would have one of these, I have no idea. I'm guessing probably something to do, because conductance is usually used for determining dissolved solid content in liquid samples. That's my guess, probably what they're using it for, environmental science, but I'm not sure. Anyway, I want to get this apart, have a look at the internals, check it to make sure it works. So I'm not going to plug this in until I've checked the internals, because when you're dealing with old stuff, especially unknown old stuff, there's a small risk it might explode. So I want to check there's no obviously bad capacitors or whatever. So yes, let's get the cover off. The only screws I can see holding it on are these 4 on the front, so we'll take them out and see what we can access. So I have got the screws out. Let's have a look at the internals. I'm assuming this is going to be held on by, yes it is being held on by wires. Can you see? So we have the back of the meter here. This is the rotary switch with a bunch of different resistors on it. This very much does appear to be fairly analog looking. Interestingly, this is a PCB. It's one of the old ones, so it looks like, or whatever they're called, is the older material, not FR4. I'm going to desolder these wires off the switch to get this separated so we can have a proper look and get the case out of the way. We'll check this transformer quickly as well just to make sure that it's still good. So I'm going to desolder this and I'll be back in a second. So I have detached the front cover. What I'm going to do first, which is important, is I'm just going to check this transformer is actually still sound, because it looks a bit crusty. I will move the camera in a second so you can get a closer look at it. It is marked a 6.3 volt secondary. There is a centre tap on the primary. I am assuming it is 240 volt. It doesn't say, but I'm going to assume. What I'm going to do is I've got my multimeter on continuity. I'm just going to check that the primary is actually continuous and the secondary is continuous and they're not shorted together. So if we measure from one of the primary to the other, we get 277 ohms-ish. And the centre tap, we get 230 ohms, and that one, we get, this is not reading clearly, but about 37 ohms. So what this probably is it's probably 0, 230, 240, or 220, 240. This centre tap is not needed for my purposes. The secondary, we get 0.3, and I'll just check. There is nothing. Good. Now, with that out the way, what I will bring in, you probably won't be able to actually see the dial on this, so I'm going to have to set it on my lap, but this is my, this doesn't fit, this is my insulation resistance meter. It's quite large, so I will clip one side to the primary, one side to the secondary, like that. I will set this to the lower voltage insulation test for starters. That's passed fine. I'll set that to 500 volts. And we're getting about a giga-ohm, which is fine. So I am satisfied this transformer is not bad. That was my worry. We can get this out of the way. Now I'm just going to check the transformer is actually working. So I will attach, this is the switch wire. I will just solder these two together as a temporary measure. Oh. There we go. I will solder those together. We will bring the multimeter back in again. Volts AC. This plug is not fitting in the socket properly. There we go. Ooh, transformer hum, but seems to be fine. If we measure the output voltage, 7.7 volt, that's fine. Primary, 242 volt. 212 volts, that's probably 220 volt winding and a 240 volt winding. But again, I'm happy with that. That seems to be working. So onto the actual board itself on the front panel. Back to the normal angle now. So this is the back of the front panel. What we have is the power switch over here. We then have this PCB here. We have a big potentiometer on here, which is marked, I can't tell if there's 1 ohm or 1000 ohms, we'll see in a second. This is the back of the meter and the rotary switch over here with various different values of resistor on it. We have the two outputs over here. This does have hallmarks of being, again, homemade, just judging by the internal construction of it. But this this PCB does not look homemade, although I might be wrong on that. What I think we'll do next is I'm going to take this PCB out. I'll undo these bolts and see if I can get it off, so that we can have a look and see what the circuitry on here actually is, and try and maybe reverse engineer what this device actually does. This big capacitor I'm slightly concerned about because it has rubber bungs in the end, which have a tendency of failing, so I might swap that out for a new one just as an abundance of caution. I see what might be paper capacitors as well, bumblebee capacitors, but I'm not sure. Again, I'll have a look once I've got the board out. So I have got this off. If we have a look carefully at the other side of this board, it is covered in some sort of varnish, which is really annoying because it means actually getting anything off of this might prove challenging. But when you look at the bottom of this, it looks very much like a homemade, well, not homemade, but hand-etched PCB. So I think this probably is actually handmade, and it's just been a hand-etched PCB for it. This, I'm going to wild guess, is probably late 60s, I think, just judging by the look of the components in here, but I'm not 100% on that. If we have a look on the other side again, I haven't actually worked out what all these parts are yet. I'll move that back in frame. We have the incoming supply from the transformer comes in here. There is a half diode or half wave rectifier diode here. It is silicon, thankfully. 1960s, it could have been selenium, and if it was, that would have been a nightmare. But it is actually silicon. We have half wave rectifying diode. There is this big capacitor which is across the power rails. I'm going to take this out because I can't get a good reading on the value of it to test it and see if it's actually still good or not while it's in circuit. We have a few resistors, a couple smaller capacitors, it would seem here. I think these might be polymer capacitors or paper capacitors, but I'm not, again, 100% sure exactly what they are. There are 4 of these packages here. Again, I'm not 100% sure what they are. They're probably some sort of transistor, I think. Actually, there's another package here, I'm not sure what that is either. And then either inductors or transformers or chokes or something. I'm not sure what they are too. I think first call of action is going to be getting this capacitor out so that I can measure it and check that the capacitor is actually still good. If it isn't, I'll have to replace it. I don't want to replace unnecessary things. Let's try and keep it original, but at the same time I want to make it actually usable. We'll see. Anyway, yes, I will take that out and I will measure it, and I'll get back to you in a second. I think getting it out is going to be a bit of a pain, but we'll see. Yeah, so I have got this capacitor out. It is definitely bad. I have measured it. It is nowhere near the capacity it should be, and it is not actually holding a charge anymore. When you hold it, you can feel it's very light, so I think all the electrolyte has evaporated out of it. Interestingly, it's an old RS logo. I've never actually seen this one before, so I'm not sure what period it dates from. But the capacitor, it says on it actually here, P6947. Guessing that's probably the 47th week of 1969, but I'm not sure. Maybe. Anyway, this is a 1000 microfarad 15 volt electrolytic axial capacitor. And it just so happens in my stock I have a 1000 microfarad 25 volt axial electrolytic capacitor, so I will I'll just fit this one as a direct replacement to that, and we should be fine. It goes to show how far capacitor technology has come as well, that this is actually a higher voltage rating than that same capacity, and look at the size difference. I'll fit this though, and we will probably power it on and see what happens, because I'm not sure what the rest of the stuff is, and it should be fine, I think. We'll see. So capacitor is now changed. I'm going to power it on. Now I have extended the wires from the chassis here so we can have it flat on the bench while I power it on. And then I'm going to measure the voltage on this capacitor here and check that it is reasonable, basically, that it's not very high or very low. So actually, where can I put my meter so you can see the screen? We'll put it there, that'll do. DC volt, because it should be DC voltage. Turn this on and hopefully no bang. No bang, just transformer hum. And then we measure the voltage across that and we get 9.4 volt. Okay, that seems all reasonable enough. I'm happy with that. Now the thing I'm going to do, I'm going to resolder the wires from that back onto the switch. I am going to put the front back on again. We'll probably move the camera from here back across. You can't see me pointing back to the previous tripod arrangement, and we will see if this actually works. We can work out how to use it. I have a guess as to how this works, but I'm not 100% sure. So we will see. One moment while I do that. So for test purposes, I have put a couple of leads onto here. I'm not sure if the switch is on or off. I'm gonna guess it's probably, we'll see. Turn that on. Yeah, it is on. Turn that off. Good. Now to try and work out how this actually works. There's nothing connected to the leads here. I have set this to 0.1, which I'm going to guess is the scale. This is probably then in, so 12 times 0.1 would be 1.2 Siemens conductivity, I think. We'll try to turn this on. That is now reading. Okay, so as I turn this, it is changing, but not as much as I would expect. If we change this, does anything happen? Methinks it is not working properly. Okay, I'm gonna take it back apart again and we'll have a look on the inside and see. One moment. So it is like 2 or 3 days later and I have finally actually managed to fix it. This is the schematic. I'll go over it quickly now. The issue with this is I reverse engineered it fairly quickly. That was fairly easy. But all of the transistor, or most of the transistor packages inside, were unmarked. And as I ended up finding out, these are germanium transistors, not silicon transistors, which was what was causing a lot of the issues, because I was getting very confused by some parts, but I'll go over it here. This bit up here is the power supply. So we have the incoming line and neutral. There is a transformer with the 220 volt tap, single diode, and the smoothing capacitor. That's very simple, self-explanatory. Over here, this is where it gets a little bit more complicated. I'll probably put this up on the screen so you can see it properly. I couldn't get it to print bigger than this. But what we have is we have another transformer, the big one on the board, with 2 transistors. The center tap of that transformer is earthed. Well, not earthed, it is to the 0 volt line. And the other 2 ends of that transformer each have a pull-up transistor with a 10 ohm resistor in line with them. And they are as part of an ASIO multivibrator. So what happens is this side of the transformer gets pulled high, and then this one gets pulled high, and this one gets pulled high, and that one gets pulled high. And it goes back and forth, and by switching the polarity across the coil, you make a sort of AC-ish waveform. Then, coming out the other side of this, we have our AC-ish waveform. There is a 10 ohm resistor in line with that. That goes to one of the output jacks. That also connects into the bottom of a chain of 3 resistors, which is a 110 ohm resistor, a 1k resistor, and the 1k potentiometer is the big one on the front with the big knob. That has the VCC going to the wiper of that potentiometer, which again confused me a bit, but what that is doing is it is not how you'd normally do it, but what it is doing is it is moving the reference point, because if you see the other end of this connects back to that end of the transformer. So what it is doing is it is shifting the 0 volt reference for the measurement voltage here with reference to that ground by moving the supply up and down this voltage divider chain. This comes out and connects into this resistor array here. We have the wiper for that connects onto here, and that goes to the other output contact. These resistors here on the rotary switch, they set the range, or the unit. This then, so basically what you're doing is you're putting a resistor between here and here when you're testing it, which is basically putting that resistor in series with this chain and in parallel, so in series with this, and then that whole thing in parallel with the known fixed value on this, basically. From the output you then have a capacitor which is passing the AC waveform. These 200k resistors here, I think, I'm not 100%, but I think what they are doing is they are basically biasing that so that you're ending up with a tiny fluctuating waveform. And what they're doing is they're going a voltage divider from VCC to ground. At the centre point of that, it is then referencing this coupled waveform. So you end up with that waveform oscillating around the middle point rather than the 0 volt reference. That then means your transistor will be much more sensitive to that tiny fluctuation in voltage. This goes into here. This is a Darlington pair, again 2 more transistors. What this is doing is taking that waveform coming out of here, amplifying that voltage, and I think converting that voltage into a current, which it then passes through this transformer. On the output of that transformer, one end of the centre tap winding is not used for some reason. The other, between the centre tap and the other end of it then, there is this transistor here, which again confused me a lot, but what this is a germanium transistor being configured to work as a diode. And with germanium transistors, because reasons, apparently the base voltage of a germanium transistor is very, very low. So when I was measuring this, I assumed that was a diode package. When I measured across it, I was getting like 0.09 volt. And that had me stumped for ages when I was trying to work out what on earth is going on, because I was assuming that was going to be either like a selenium diode or some sort of diode, which would not have a volt drop that low. Then I was thinking, is it a MOSFET? Because you can do that with a P-channel MOSFET. And anyway, once I worked that out, what you have is that capacitor, I think, should also be 470 picofarad. I just forgot to change it on the thing. But this then goes through that meter. I think that is how this works, but again, I'm not 100% sure. I had to call in a couple of favours from Big Clive and Acular in order to explain some of the germanium transistor stuff, especially to do with this transistor diode thing. I've not seen that before, but apparently it was fairly common at the time. Anyway, with that out of the way, I have got it working, I think, so I will show you that now. So I have done a bit of research about what this device was probably originally used for, and I think that this was probably an environmental science piece of equipment, probably used for measuring dissolved solid content in water. So it can tell you like salinity or lead contamination, other basically dissolved solid content in liquid, I think. The way that I think this is supposed to work is you would set this knob to one of its ends, and this all the way to 0. I have connected a jar of salt water here with a couple of wires in it as a test electrode. This is not precise, they would usually be a set distance apart, usually 1 centimetre, but it depends on what you're trying to measure. What you would then do is you would turn this on, and if you cannot, so I turn this, it does not go to about halfway, so this is wrong, still off, there we go. See, so that's gone to halfway there when I set that to 100 micro. As I turn this, it goes up, and as I turn it back, it comes down. So when I set it to 1, that's on half, so 100 microsiemens is my measurement. And then when I turn this down, again, you can retune it back to 10, and it goes back to half. So this is 10 times less, 10 times bigger reading, same reading. This is, I think, how this is supposed to be used, but I'm not 100% sure, so if anyone knows better, please let me know in the comments, because I'm open to correction on that. I have compared the values this thing outputs to the values of my multimeter, and they are in the same ballpark. I think the reason for the difference will be the fact that this outputs about 10 volt AC, and my multimeter outputs like 2 volt DC. So there is quite a substantial difference in test voltage between these two. This is measuring AC, that one's measuring DC. This is probably built in the 60s, and my multimeter was bought off the shelf a couple of months ago. So the calibration on this has probably also wavered a bit. But I think I can call that good. I have got a reasonably sensible readings out of it from what I can tell. They correspond fairly well with what I'm getting off my known calibrated meter. As I say, any more suggestions, information about this, please let me know in the comments, because I am very interested. But with that, I think I'm done here, so I will see you in the next one. Thank you very much for watching. Bye.